think it's time to get going. So we were talking about mass spectrometry, the different parts of a mass spectrometer, and that's kind of what we're still working through. The good news is we're coming to the last part. How's that? And that's where we're blowing these molecules into bits and fragments, whatever we want to call them, and they have a charge on them. So there's some negative, some positive, some neutral. And we always look for the positive ones, or I shouldn't say always, but generally we look for those positive fragments. A few cases where we don't see much difference in positive, we will look at negative, but that's pretty much rare. So kind of our next step, we've separated these, so coming out of our mass analyzer, we have simply one mass, one charge at a time. We want to count them. How many of those ions? Then we go on to the next fragment, the next piece, next mass, and so on. And so where we benefit so much from this detection method or from this technique as a whole is that we are looking at ions. We are looking at ionized materials. And so we have, once you know, an ion detector, an ion multiplier, which is really, really neat. And it's neat in the sense that when an ion collides with one of your collector cells, it gives off 10 or 20 times for that. And then you have this one focused to this one. So then there's 10 or 20 times what that one gave off, and 10 or 20 times what that one gave off. And by the time you get it through a cascade of these, you've got a tremendous number of ions that you can count. And that's where we get our sensitivity from. Basically, the fact that we're measuring ions, and it's easy to multiply them so we get a countable signal. So we'll get to data interpretation. You know, as I alluded to before a couple times, if somebody does this for a living, 24 hours, well, maybe not 24 hours a day, let's say only 12 or 15 hours a day, you get pretty accustomed to see these fragmentation patterns, and you start understanding what happens to come from what. And you can actually start putting molecules together simply by knowledge. This is a very, very simple spectrum. I showed you carbon dioxide before. This happens to be acetone. Here is the molecular weight of acetone, a mass of 58. And it gives up readily in this fragmentation, it gives up the methyl. So 15 mass units down, here's another ion. If we would look at losing the H3, we have a fragment here, 24, 27, that would be counted. And here's a methyl group that's given up from this ion here. So you find characteristic fragmentation patterns of each of these molecules. And like I say, with enough experience, you kind of put them together and understand them. We have pretty much two, many different categories of mass spectrometers, but two major categories. One are low resolution instruments, and that's what we see here. We see a mass of 15, a mass of 27, a mass of 43, and so on. And you know, that's not exactly right, is it? Only carbon has a mass of 12. Everything else is something else, is 14 point something, and so on down the line. So this is just kind of rounds these things off. It isn't really very good discriminating. It lumps anything with a mass of 15 together as 15. And that could be 14.999, it could be 15 point something, something, something. It could be different molecules, different combinations. So what we really have is a nice technique that separates those masses, mass 15, into very, very fine, you know, hundreds or thousands actually, of a mass unit. And then there's only some possible combinations that you can have. So at this point, if we would look out here at N2, you would see there is a mass of not 28, which could come from CH3. 28. Probably got to get another 13 or whatever about it. But anyway, it could come from different places. But if it's 28.005, it can only come from nitrogen. Now we start getting molecular formulas. So we don't just get a fragment to look at, a piece to look at. We know what the elemental composition, or atomic composition is of that particular peak. And so it's really a powerful tool. The problem is they tend to be more expensive, they take a little more effort, and so Most of the instruments you see around are low resolution instruments, but these are very, very useful instruments when you can afford them and need them. Computer assisted searching, so let's say you're not a person who lives with mass spectrometry every day of your life in dealing with the data, and so you just want to come in and use it. I want something identified in my sample. Well, what you do then is this, your computer gets all of your output from your mass spectrometer, and it looks at all those pieces and searches through its database. What molecules will give you the same pieces that you just found? And so the computer will do a search for you, and it'll turn out and rate the best matches. It'll say, okay, the most likely probability is this compound is this. It could also be that, or that. But so it ranks them in terms of how well they match. And this is where it takes a little bit of thinking about, because the computer will always give you that answer. It'll always give you matches. And they may be the dumbest choices in the entire world. It may not relate to anything entirely possible, but it's the best match the computer came up with. And so when you get data from a mass spectrometer, you sit and look at it. Does that make sense? Might I have found this in my food? Then you might even look at things like, well, this came in from a gas chromatograph. It's where it diluted, where it came out of the gas chromatograph reasonable. Would the compound like that come out diluted out of it here? And is it possible? So you still look critically at it. It's a black box that spits out a number, a name for you. I have a really nice example of that, where I was at the American Chemical Society meeting, and a scientist from UC Davis was presenting flavor compounds that were found in pineapple wine. And so the tradition is, of course, to simply list all the compounds you found. And back in those days, you'd see lists of maybe 100 things, one slide after another slide after another slide. It could have been much more boring, when you think about spending your time watching people name things. But I was kind of sitting in the audience looking at it, and turns out that one of the compounds was butanol, that was butanal, and then he listed ethanol, and then he listed a couple other things, and butanol again. And I'm thinking, that can't be right. That can't be right. There's something wrong here. He wasn't bothered to list by it. He just went through this one first, and I kind of raised my hand and said, did you list these compounds in order that they elute from a gas chromatograph? Because that's mass spectrometers being fed things. One comes out of the gas spectrometer, goes in the mass spectrometer. And so they have to come out and be listed, typically, in the order they elute. And he said, yep, that's how we did it. That's normal. Well, how did you get butanol eluting before ethanol? That seems impossible for me. And by the way, you've got normal butanol listed twice. Are there isomers of normal butanol that I don't know of? Well, no. And he said, well, these are what the computer said. Okay, so they're probably not correct. Well, maybe not. You don't ever want to be put in that position. You don't want to be put in that position. And if you're in the audience, you're kind of torn between kind of bringing up something you really don't want to. You don't want to raise questions and embarrass anybody in public. And by the same token, you don't want anybody to sit there and believe that was correct. So kind of how do you manage? You do it as politely as you can. There's been times when you come and speak to somebody after a meeting, and that's also another way to do it. But anyway, the machine gave matches, and they were unreasonable matches, but they were the best matches, and he simply reported them without thinking about them. So again, you have to use care when you let the computer do the thinking for you. You really have to give that thought. So interfacing the mass spectrometer with various chromatographic methods, that is, of course, the easiest way oftentimes to get things done. It isn't very often you have a pure compound that you can put into this little probe and put it into the mass spectrometer and get some view of that pure compound. You're typically in foods working with complex mixtures, and you want to know what that mixture is. And so what do? You feed your mass spectrometer from a gas chromatograph or from an HPLC instrument. And so that creates some problems, because that mass analyzer And for that matter, oftentimes the source, not always the source, but the mass analyzer has to operate under a vacuum. 10 to the minus 6, 10 to the minus 7 atmospheres. That is an extremely good vacuum. Why? Because you just ionized all kinds of things, and you're drawing them into this chamber, and if there's air in there, they collide with air, and the ions are gone. You didn't get any results. So you've got to have an absolute air-free, nothing else in there. These ions are going to collide with. That way they live long enough to be separated. So you need a high vacuum. Now, how the heck do you get the system to operate under a vacuum when you're pumping gas chromatography carrier gas into the system? And you might say, well, if you think about it, maybe I didn't get flows, GC flows, or gas chromatographic flows, but they may be 2 mils per minute. Okay, you think that's not a lot. The vacuum pump should be able to pump that out, maybe. But if you think about what that 2 mils is, volume, if you put it under 10 to the minus 6th torr, it's one heck of a volume that you have to pump out of there. So there are issues. You think about an LC, what do you have? You've got a pretty ugly eluent, or a mobile phase for liquid chromatography. You can pump this liquid in there? You know, there are problems. That's where our challenges come. How do we get rid of that mobile phase so you can operate your mass spectrometer? And there's really different systems that have been done for this. We are fortunate in gas chromatography. Back in the olden days when we had packed columns, big diameters, high mobile flow rates, you'd have 20, 30 mils coming out of this, 20, 30 mils per minute. Dumping in here, we couldn't do it. Today, when we use a capillary column and a very, very small capillary column, we can simply run this effluent directly into our mass spectrometer. So it's a simpler task today than it ever was before. And so it is mainly a direct inlet. Here's our capillary column, but it has to be a fine, a really small diameter capillary column, and we can manage with this approach. You do have good vacuum pumps, obviously. There's always a roughing pump that takes out the majority, and then there's a second pump that will then take the turbo pump or diffusion pump. So a turbomolecular diffusion pump. And basically, they can manage that kind of flow for us. This is a diagram of a turbomolecular pump. We're not going to lose any sleep over that one. So, okay, and I got ahead of myself. Here's the calculation. 1 milliliter per minute of gas flows is 10 to the 6 milliliters per minute. The pump has to pump out. So that gives you an idea of the difference between something at atmospheric pressure and what we have to pump out of that mass spectrometer when we're dumping it in. So we really do need good vacuum pumps for this system. But they are a standard detector these days. Here's your capillary column fed directly into the mass spectrometer. It's fed into a quadrupole mass spectrometer. There's, of course, a detection system and ultimately a data handling system for it. I've shown you the top part of this figure before, and I don't remember if I said anything or maybe I didn't present the bottom. I guess you did see the bottom one also, yeah. And so, I mean, this is the type of data that you get out of it. This is coming out of your mass spectrometer. It's simply counting out how many ions are there at mass 29, 38, 39, 40, 41, and so on. So you do get this mass spectrum out of the system. Since we've talked about this before, I won't bother anymore, but they are doing matching, the computer's doing matching, again, between the library spectrum and what it picks out of a complex spectrum up above. HPLC probably is one of the hottest areas of food analysis. And if I would say why, I would say I'd have to be kind. I sometimes do tease people that like LCs. I would say because they're so far behind gas chromatograph, but that might offend. Are you still here?
Yeah.
Can't help myself. It is, I've said gas chromatography is mature. we've met and matched all theoretical possibilities. LC is not there yet. It is still in the development stage. Progressed a great distance also, but there's still room for improvement. People for a long time have had gas chromatographs, but it's more recent for LC and LC MS systems. So there's really a lot of opportunity here for improvement and for application in our industry. The problem we run into, of course, is now we're not pumping a milliliter of gas. We're pumping a milliliter, perhaps milliliter minute of liquid into our system. And so we have just a lot more mass we're pumping in that would turn into a tremendous volume if we simply put it into the system. And so we have to have some kind of a special inlet system to separate your analytes from what I call a carrier, or if you want to call it the mobile phase. So we have to have special systems for that. We do have an opportunity of analyzing air samples, and we do make use of measuring air samples in our field by mass spectrometry. So in that case, we're just drawing air in from someplace, the environment or wherever, into the system. So that's a fairly easy one. When we get down to other techniques where we're pumping the liquids, then we do have these types of techniques. When we use a mass spectrometer in my laboratory, it's very commonly one where we're measuring what you breathe. And you might say, that's kind of interesting. At least I hope you think like that. Because I'm interested in flavor, and a lot of flavor are volatile compounds. And historically, what we've had to do is we've given you a food, and maybe it's so many parts per million of spearmint flavor. And you put that into your mouth, and that's fine, and you swallow it. And we just gave you so many parts per million. And we say, oh, you responded to. You responded to so many parts per million in the food. But it's not what's in the food, it's what's given up to the breath to get up here. And so our techniques now permit us to measure the stimulus that you were given up in your olfactory region. So we take the inlet of our mass spectrometer, put it up your nose, then you swallow that beverage or that food, and I can tell you exactly what stimulus you were given and what you respond to. So we've taken the food out of it because most of our flavor ends up in your stomach. It's gone. It doesn't get released for smelling. You swallow it, it's gone. So we're really interested not what's in your food. We're interested in what's given up by your food during the eating process. And it's a tremendous technique for that. It gives us the ability to look at those relationships between people and perception and stimulus. It's a fascinating tool for us. But okay, getting back to LC, since that's the topic. There's different techniques, electrospray, thermospray, particle beam interfaces. Again, different ways of looking at those, getting rid of the mobile phase. This is an electrospray source. The source is, of course, where we form those ions. And so we'll have our effluent from our LC coming down the center. We have a gas, typically nitrogen gas, that's coming along the side of it, and it'll basically vaporize that effluent of it. This, your center is going to have, this central column, it's going to have an electrical charge of about 4,000 volts on it. And so your droplets that get sprayed out, that spray is going to have a lot of charges in it because of the high potential it comes through. This is under a vacuum, and so the solvent is evaporating, and so you've got this momentum, of course, we've got things moving out this direction. And so in a vacuum, you're going to start evaporating your solvent, and you're going to be left with a charge. That residual charge has to go someplace. It tends to get deposited on your analytes. And so you're left with your analytes here and the solvent being drawn off. And those analytes are still moving. They're given a velocity, and they get sucked in either by electrical charge, the 25 volts of the opposite charge. So they draw in this direction, and then they go into your mass spectrometer. And so basically you more or less evaporate your solvent off from the system, leaving the charge you put on it on your analytes, your molecules. So it's really a gentle technique. You don't see a lot of energy, a lot of things exploding into lots of pieces. But a nice technique, a very, very common technique. This is the atmospheric pressure chemical ionization, APCI, atmospheric pressure chemical ionization detector. And this is the one we use, so we're sticking this up someone's nose back here, drawing in the breath as you breathe. And instead of having a charged column through here that you would have in your LC effluent, there's just a nice little needle right here, a needle tip that has about 5,000 volts on it. So whatever air, whatever's passing through here, goes through 5,000 volt electric field. And again, that ionized molecules, and they go then into your mass spectrometer. So there's different ways to do it, different types or different ways to get the solid, but that's basically what you're doing in your mobile phase. You're trying to get rid of it one way or another, so you end up with just your analytes. This is kind of how your spectra are displayed in that sense. Your LC is drawing some kind of a pattern. This could be monitoring refractive index of compounds as they come out of your LC. It could be monitoring 280 wavelength, looking for UV absorbing compounds. So it could be UV detector or some other type of detector. So it draws your chromatograph. And then your instrument, your mass spectrometer, is taking a complete look at all the fragments that are coming out. And it can be several times a second if you've set it up that way. So you're getting a mass spectrum. What are the fragments as we go along through this peak? And so we get to kind of two-dimensional. We get an idea of retention time and elution time, and then we get a look at what fragments are there. Yes?
So the total ion chromatograph that we see up here, does it necessarily need a HPLC detector to see it, or just sometimes you just link your LC directly or GC directly to the MS?
Oh, right.
If you're in the total ion chromatograph mode, you can still see this. Do you really need another?
Yeah, you don't have a gas chromatographic detector or an LC detector necessarily. You could,
Yeah.
but you normally don't. No.
You can still get total
Sure.
ion chromatograph.
Because you're always blowing things apart, you're always forming ions, and you skim off a certain percentage of those ions, and you just measure a certain percentage. Okay, there's more ions, less ions. So you're more or less taking a sampling of it in the mass spectrometer itself. So that's not generated, you're right, by the chromatograph. It's generated by the ions in the mass spectrometer. Sure. There's a lot that can be done with quantitative analysis. One of our favorite techniques, and by far the most costly, is to do stable isotope analysis. And by stable isotope analysis, you know, when you think about it, and I don't know how much time you spent in that area yet, but you want to have some anchor. So let's say in my business, I'm interested in benzaldehyde, cherry flavor. It's formed during the Maynard-Browning reaction. So I really want to measure benzaldehyde that's in my sample for some reason. Well, if I were going to have some kind of a reference compound to put in my sample, some reference for quantitation, I know my reference is this much, my peak of benzaldehyde is this much, can I kind of use that as a key? That's oftentimes how we do it, but there's nothing better than spiking your sample, taking your sample and putting some benzaldehyde in. It has carbon-13 labeled, so it has carbon-13 in it. So your internal standard, your reference compound, is the same compound you want to measure, but it's got maybe 3 carbon-13s in it. And the mass spectrometer is absolutely great. Remember, it's plotting mass, it's looking for mass. So we could come along and we could plot mass of 106 for benzaldehyde. But if we were having the mass spectrometer look at 109, then that would find the benzaldehyde we put in at a known concentration, and we would get a peak for that. So it's really neat. Your reference is the same compounds if you think of using internal standards and quantitative purposes. So you can actually compare the two areas. If the area of your spiked sample is the same area as your peak for benzaldehyde, you'd say they're the same concentration. Or, you proportion it. If it's 1/3, what you put in is 1/3 the concentration. There's no better standard than the compound itself. Ben?
But even it's an isotope label compound, it will still elute the same time as your normal.
Yeah, so let's say it's a mass of 106 and now it's 109. That's a really small change. There may be a really subtle difference between them. And you would expect that because your mass spectrometer is going on monitoring 106 and 109.
It will pick up.
So it is a hair earlier, it comes off of your instrument. It elutes a little bit faster off the gas nanograph, the 106 and 109. And they fragment just a little bit differently, but it's so close, there's no better alternative. The only problem is it cost me $10,000 to get my 109 benzaldehyde. And I want to look at 20 compounds. Let's see, 10,000 times 20 compounds. We got to go back to the granting agency, get a little boost there. Someplace along the line, we need $200,000. And that's the reason why it tends not to be used very much is the cost.
How about making your own isotope? Would you
Dabble in chemistry? Sure. We do. We've done that, that's right. So you synthesize the compound yourself. And there are companies like Cambridge Isotopes that also make them, but they're really, really dear. But you can synthesize them, you bet. Just have to have somebody who's a good enough organic chemist. Maybe you take organic chem 3 instead of 2, how's that? Or 4, or 5. But it's like I say, it's really nice example. Well, I guess the one that's here is for 5-fluorouracil. And so here's a sample that I have to take a look at. And if we would go ahead and label this with this nitrogen with a mass of 15, and so this would be our spike, we can differentiate what has a mass of 1 mass higher than this. So again, this is a normal sample coming along, drawing how much of, and I don't see the mass on this any place, but that doesn't help me a great deal. So anyway, this is the same compound, 1 mass higher. It doesn't see anything else. It doesn't see the rest of it. All it does is see the amount that you put in, and by proportioning, it works. And I should put the mass on there so I know what the heck it is. So purity of a GC peak, or an LC peak for that matter, is really important. So as I mentioned before, we've got something like over 6 million compounds identified, logged into American Chemical Society. And so you're doing your analysis and you'll get a peak right there, another one right there. What makes you think that there isn't one of those other 6 million compounds that happen to also come along at that very same time, at that very same place? And there's a good chance it will, right? And so really having a mass spectrometer that looks at that peak and is scanning that peak, is there one compound? Does it have exactly the same spectrum as the compound you want to measure or not? An issue with this is benzene. We have a limit in foods of 10 parts per billion benzene. And we've worked with people before that then are running gas chromatography to monitor their food or these products for benzene. And if you say, gee, this contains benzene, it's a reject, and it doesn't because you didn't know the purity of that compound that you're measuring, you get yourself in an awful lot of trouble, or you approve something that you shouldn't approve. So it is really important. The mass spectrometry is really good for knowing whether or not you got the compound you think you do, and only that compound that you think you do. We have, of course, the ability to do mass spectra on mass spectra. And so that may sound a little bit weird, but it goes back to, here's a mass spectrum of a compound, and these are different masses as we go along here. And as I said, on a low resolution instrument, you can have many different compounds, molecules, that make up a specific mass. And so you may well be interested, 2 compounds may have very similar spectra, So you start selecting, okay, I'm interested in this particular ion fragment. What is that? It's 136 mass. There's about 9,000 compounds that have that mass. So what do? Is I focus this, so this particular fragment gets bombarded again and broken down to see what it is. So you can get a whole bunch of spectra, and you can start taking apart each one of those pieces and make sure each piece is correct. It's a tremendously powerful tool in many different ways. And this is what we call a triple quad mass spectrometer. And it really is one that has a single mass spectrometer here, selects a particular fragment, a piece that was blown up, and bombards it again here and measures again it here. So again, just insurance, you're measuring what you want to or what you think you are measuring. Lots of different applications in foods. I mentioned this one already, the aroma release in your mouth. How do you measure truly what makes up a olfactory region? Identification of unknowns, assurance of purity, quality analysis, quantification of various analytes. Adulteration is something in your food that shouldn't be in your food, and you want to prove that it's there or not there. So there's really a lot of nice applications of this technique. I guess this is one of the applications also that we took a look at. Determine the effect of replacing a bulk sweetener sucrose with aspartame on aroma release profile. Does a sugar sweetened beverage taste like an aspartame, a high potency sweetener beverage? Is there a difference between Diet Coke and Coke? Does it change? It does. Very much so. Why does it change? Do you ever think about that? Why on earth does it change? It's you put exactly the same flavor in there. One, you take the sugar out, then okay, but you put the sweetener back in anyway as a high potency sweetener. That was one of the things we were interested in back at one time or another. And so we had 3 different beverage bases. One beverage base had no sweetener in it, but the flavor was added to it. Another one was sweetened by aspartame. Another one was sweetened with sucrose. So we have our 3 different models. And of course, they were diluted to appropriate concentrations. And this is actually one of the founders of this technique. What he's doing is he's sitting there, and this was our particular 3 beverages. He takes a sip in this straw, and sips some of the beverage in, swallows it. Have you ever noticed, have you ever paid attention to this? Do you know that you always exhale after you swallow? I don't know if you're very conscious that you think about it. And that's what we call a swallow breath. And that's what makes you understand what you just swallowed. Because all of the aroma is going down your throat. It's not going up into your olfactory region. But when you exhale, you give this boost of chemicals out here. And so that's what the mass spectrometers measure. Hold up his nose. So anyway, he's drinking, swallowing, and then the mass spectrometer is measuring what stimulus he was just given. And this will look rather ugly to you probably, but let's see if we can't make it somehow comprehensible. What this is actually what the mass spectrometer is spitting out as the fellow is sipping on his orange juice and swallowing. And this is actually monitoring acetone in this breath. Acetone is a product of metabolism of our body. So there's nothing here because he was exhaling. No, he was inhaling. So he inhaled here, so you're drawing air in. There's no acetone then, unless it's in the room. Then he exhales. And so from your lungs comes the acetone. Then, of course, he's inhaling again, exhale, inhale, exhale. So essentially, the mass spectrometer is taking track of this breathing profile. And that's kind of a reference. And so this is then looking for different flavor compounds that happen to be present in the food. So the mass spectrometer, in this case, is looking at an ester, a very fruity component, very volatile component. It doesn't want to be in the food, it wants to be in fruit. And so he hasn't had any of this yet. He's just sitting here breathing. At this point, he takes a sip into his mouth. He exhales after swallowing. And this is then a second one, and a third breath, a fourth breath, and then it's further out. So what the mass spectrometer said is, boy, you got a big shot of this aroma chemical. That's what was given up here. That's a different aroma chemical. So these 3, 4 chemicals are really quite volatile. They really want to get rid of it. And then here, some of the, what I call heavier, less volatile chemicals. They weren't hardly sensed at all in that swallow breath, but they built up over time. So it's kind of a temporal profile, a difference in how flavor chemicals are released and how they're sensed. But I say it's a rather neat technique that helps you kind of understand what you were given and how that relates to perception of the food. So that mass spectrometer is a pretty neat little tool. Purity, GC, HPLC, how do we know a peak is pure? Right, we do a mass spectrometer. We don't know what that is. We think we do, but we don't know what it is until we put some effort in ensuring it is what it is, and that's mass spectrometry. Adulteration, again, we've had a lot of examples of adulteration. You know, there's much more natural vanilla sold there is grown any place all over the world. Much more natural sold. And you think, how can that be? What's the major component of a vanilla extract? Vanillin. It's about 1% of vanillin. Vanillin's cheap. So what you do is you put a little color in there, you put a little, artificial vanillin in there, and you sell it for, $80 a gallon. It's not a bad business. But what do? You look at it in terms of mass spectrometry. It's that's a fun one. Vanilla is the most adulterated flavor in the world, and that's because it's the most popular flavor in the world. And like I say, there just isn't enough vanilla grown. We're going into a real crisis of that too. It's I don't know if you follow any of the websites that talk about trends today and issues today, and they just had a long article on vanilla, and there just isn't enough of it to go around, and what's happening to the cost of that. So it's a fascinating one. So adulteration, useful for this. We're of course interested in pesticides, run routine pesticide work. You want to know what pesticides are there, mass spectrometry. Contaminants, odorants in food, so again, all kinds of issues along those lines. Pyrolysis of microorganisms. You can identify microorganisms by mass spectrometry. You pyrolyze the microorganism, and you look at all the bits and pieces that come out of that microorganism as it's burned. First we burn it up, and then we blow it up. How's that? A great tool to make sure it's sterile. So again, pyrolysis, very, very high temperature, very quickly, 0.5 seconds. You go up to 770 degrees centigrade. So it pyrolyzes, it basically vaporizes it. And then you put it into a mass spectrometer and you can look at the fragments and identify the microorganism, where did they come from. You get mass spectrum for Staph aureus, for example, different mass spectrum for Escherichia coli, so E. coli. So it's amazing in that sense. You want to look at mouse brains. I'm not quite sure why. Maybe you're looking for drugs. You get a drug therapy. Does the drug make it across the barrier? And this is cross-sectioning a mouse brain. Then using a mass spectrometer, kind of like the DESI, you bounce it off, reflect it, what do you measure? And you can go along with very fine resolution and find out where drugs are, for example, within the brain. Probably not not up our alley for that matter, but again, a nice technique, very powerful technique. Using mass spectrometry show chemical composition at some place. Again, things like this are done on wheats or on, looking at what is a wheat and what's the composition of it, or other cereals and so on. So again, it's really a growing technique in the food analysis. Cost has come down. Actually, I've operated the mass spectrometer for 3 years. That's what I got paid for at Penn State when I was doing my doctorate degree. And of course, the thing was massive, as you might imagine. Now you can't quite put it in your pocket, but darn near. But massive, and the cost was equally massive. Cost has really come down. They're easy to operate. They are turnkey systems. You have to keep in mind ease can be also a hazard. Anybody thinks they can do it without thinking about it. computerized databases, data handling, advances in instrumentation. Really, like I say, there's a lot that's been done that explains why it is such a popular technique. So, with that, there's some references that I took the presentation from, so you can take a look there. So, I'd left you 10 minutes. You gonna change the exam now? So, no.
I'm gonna have them have good weekend, right?
Yes.
Okay, but before you leave, I just want to quickly show you what you're gonna do in the lab next week. So please take note of that. I will send my regular weekly reminder, but next week is again rotational lab, so you're going to be doing some groups will be doing atomic absorption, another set of groups will be doing mass spectrometry. So group C, F and G will be doing LC-MS, and all of you past couple of weeks, we got a glimpse of what you're going to be doing with the LC-MS. Remember the chromatogram of isoflavones that I showed you? We're going to carry it a step further and do identification work with MS. So for the groups on AA, we have not started spectroscopy yet. But I know with food analysis, sometimes because you only have one lab in a group, in a week, but you have 3 lectures, so we not always par with lecture and lab. Sometimes it's good to see the practical before coming to lecture. You know, some people think that the lecture is better before lab. I actually feel like visual is better before lecture, theory. So think about it as a positive, not a negative, that you're going to do the lab before lecture. So keep that in mind. I have a YouTube video that I found online for AA. I will post it on Moodle. Just it's about 8 minutes long. Just go ahead and it will get you prepared at least to what we're going to do with the atomic absorption. Basically, we're going to analyze calcium and iron in different products. So each group will be assigned a product. Again, in my email, you'll find which group will be doing what product. And that same product will be doing all proximate analysis on. So by the end of 3-4 weeks, you have analyzed everything in that product, whether it's fat, moisture, ash, protein, carbohydrate by difference, and minerals. On that one product, you'll be very intimate with that product by the end of 4 weeks. So pre-lectures is already on Moodle. You need your laptops. AA groups, please bring your laptops with you. We're going to do calculations in lab. Calculations can be tricky, so I like everybody to do the calculations at the end of the lab before leaving lab. That will be very helpful for you guys when you're preparing your report. So with that, you have 5 whole minutes free. Have a great weekend. Yeah. Do you want it?
No, probably not. It'd be best if I didn't.
Okay.
Walk back.